Assalamualaikum and hi. Before I start my introduction, first of all, I want to introduce my team members. We are from Group 8. We are three members. First, Alexander. Second, Jamie. Third, me, Aiman. So we present about the proposal page 3, which is the fire suppression system design. For the introduction, this project apply fluid mechanics principle, which is such as the Bernoulli equation and heat loss calculation. To design a fire suppression system for a 3-story building, our goal is to determine the optimal pipe diameter and pump performance required to deliver sufficient water pressure to the highest floor. For problem framing, point 1, which is the catastrophic fire risk. In high-rise and multi-story building, fire present a catastrophic risk to all occupants. Once an ignition occurs, deadly flames and toxic smoke spread rapidly upward to vertical shaft and stairwell, quickly blocking critical evacuation routes and creating immense panic. A delay of just a few seconds can trap people inside the upper floor, drastically shrinking their chances of survival. In this critical moment, as temperature spike and smoke density rises, active fire protection becomes our absolute primary line of defense. Therefore, ensuring an immediate, automatic, and highly reliable water delivery system is not just a matter of regulatory compliance or hitting numbers on paper. It is strictly a matter of life and death, serving to control the thermal energy before it causes full structural failure and mass casualties. Point 2, which is the hardest to supply area. From a fluid mechanic perspective, the highest floor of the building is always the hardest to supply area because it is located furthest from the water source. To deliver water effectively to this zone, the floor must overcome massive gravitational resistance known as elevation heat. At the same time, the fluid faces high frictional heat loss as it travels through long vertical riser, bends, and isolation valve. This accumulated resistance results in a severe drop in pressure before the water can even reach the sprinkler nozzle. For the point 3, which is the consequences of incorrect pump selection. If we select the wrong pump that fails to match our required flow rate and heat, the consequences are devastating. Under insufficient pressure, the system will experience a severe operating drop. Instead of discharging a high-velocity fire suppression spray, the nozzle will only produce a weak water trickle. This technical failure completely destroys the system's ability to control the fire at an early stage. Consequently, this leaves critical zone unprotected, leading to catastrophic structural damage and an extreme risk to human life. Therefore, to eliminate these engineering risks, precise hydraulic calculation are an absolute necessity. I think that's all of my part. Thank you.
My name is Alexander Yuzen King. 108794 is my matrix number. Now I will continue with diagnostic finding parts. First, hydraulic analysis. Let us look at our system requirement. Our analysis showed that if we want to supply water to the top floor, we must overcome a total head loss of 3.748 meter, which account for both major friction losses of 0.678 meters and cumulative minor losses of 3.07 meters across our 12 pipeline fittings. Next, let's move on to the structural integrity and elbow forces. While hydraulic efficiency is vital, we also prioritize structural safety by performance a momentum analysis on the 90-degree riser elbow. We calculate a resultant forces of 1036.49 Newton, which is equivalent to hanging a 105.65 kilogram wedge directly on the pipe. Without support, the pressure shock from water hammer will cause several vibration and eventual joint failures. Therefore, our design mandates a concrete truss block or heavy-duty steel base cleared to anchor this point and ensure long-term stability. Next, let's move on to the system performance validation. As you can see on this performance chart, the intersection of our system curve and the FP200 pump curve give us an operating point at 3.3 liter per second and 12.5 meters. This confirms that our selected pump is optimally sized to deliver the required flow to all 4 sprinkler nozzles simultaneously at the top floor. And that's all from me. Next, I will pass the floor to member 3 to detail our final installation proposal and closing recommendation. Thank you.
Hi, my name is Jamie Enajong. I am one of the design pipe engineer for this system. In this video, I'll explain to you the exact reason why the diameter of the pipe is chosen, and then the plot of graph given, and then I will summarize about the report that we have done for this pipe system. So based on everything me and my group have discussed and calculated, we came up with a new design for the pipe network to ensure the system is safe and sufficient to be used. For the pipe size, we have adjusted the value aligned with the pipe system. The main pipe I like to have the reduction of the major losses, while the diameter of the pipe nozzle are smaller to make the enough pressure disperse the water through the nozzle. We do avoid over-design the pipe to reduce cost making the pipe system working. As you can see from the graph given in the presentation, we can see that the operating point of the pipe system works at the 3.3 liter per second at 12.5 meter head pump. With that being said, the 90-degree elbow created force when water changes its direction flow. After calculation is done, the force is stable for the system pipe design. The system pipe can overcome the force and causing the system pipe to function in a long run. Overall, the pipe is well designed so that every nozzle receives the same and enough pressure to disperse the water. To conclude, this design is safe and efficient and perfect for implementation for the pump system. That's all from me. Thank you.